As we advance towards a computerised model of corrosion control, we begin to view energy flow not simply as electrons through metal, but as a universal principle that links matter, life and behaviour. The same laws that dictate electrochemical reactions in buried pipelines also govern metabolic processes in living organisms and the transfer of information across neural networks. When viewed through this lens, corrosion science becomes more than an engineering discipline. It becomes a framework for understanding how systems consume, transfer, lose or conserve energy at every scale. In this way, the physics of entropy and the chemistry of electron exchange form the underlying logic that unites technology, biology, and even social systems. By mapping corrosion reactions digitally, we replicate the logic of the universe as expressed through energy gradients. The computer, limited to binary operations, becomes a precise interpreter of these gradients when the input data is structured correctly. Probes such as the half-cell, pH sensors, isopotential devices, and especially the Alexander cell supply this structured information. These instruments translate complex electrochemical conditions into measurable variables, allowing algorithms to simulate cause, effect, and likely outcomes. In doing so, we create a mechanistic language that a computer can understand without ambiguity, something that human interpretation alone cannot consistently achieve. Dynamic modelling through the cathodic protection network dynamic project demonstrates that corrosion is not random. It follows predictable patterns when the right parameters are monitored continuously. With adequate historical data sets, the computer can recognize signatures of risk and stability, triggering protective measures automatically. This level of automation is not merely a convenience, it is a requirement in a world where infrastructure spans vast distances and operates under conditions impossible for humans to monitor in real time. The technology transforms corrosion control from reactive maintenance into proactive, self-correcting system. As we refine these computational approaches, we approach a broader scientific question. If we can model the energy flow of a pipeline, we can also model the energy flow of larger systems, ecosystems, societies, or even the planet itself. Earth's magnetic fields, atmospheric chemistry, tectonic activity and biological processes form a network of interacting forces, not unlike the electrochemical circuits we study in metallurgy. Understanding these systems through the language of energy and data brings us closer to answering whether the Earth behaves like a living organism and whether the cosmos itself follows comparable principles of evolution, decay, and self-regulation. Ultimately, computerised corrosion science serves as a microcosm of the universe's larger processes. By mastering the flow of electrons in metals, we glimpse the processes that shape stars, planets, organisms, and societies. The journey from the Big Bang to geopolitics is not as disconnected as it may seem. It is a single continuum of energy seeking equilibrium. Through digital modelling, we create tools that help us observe this continuum with clarity, precision, and other predictive power, translating universal laws into actionable knowledge that protects our infrastructure and deepens our understanding of existence itself.